everyone, welcome to my talk. Our paper, SeqGrowGraph, Learning Lane Topology as a Chain of Graph Expansions, is a collaboration between Watanabe and Xi'an Jiaotong University. I will present this work in 4 parts. Firstly, research background and motivation. The growing development of autonomous driving has increased the demand for accurate modeling of road structures. Road structures include not only explicit elements such as center lines, road boundaries, and traffic signs, but also implicit topological relationships, particularly the connectivity between road center lines. Traditional methods fall into detection-based and generation-based approaches, each with notable limitations. So let us consider the following question. How do humans construct lane graphs? Rather than perceiving the entire graph at once, people typically begin at a single point and incrementally add new elements, extending the structure step by step while connecting each new component to previously established nodes. This intuitive, human-like process inspires a novel formulation. We model lane graph construction as a sequential, step-by-step expansion process. We employ sequence modeling techniques to capture the incremental updates to the graph's adjacency matrix. Secondly, detailed introduction to our method. Let me briefly introduce our method. The framework incrementally constructs the graph by adding one vertex at a time and expanding the adjacency matrix. As a result, it flexibly models complex real-world road structures, including loops and bidirectional lanes, without requiring extensive pre-processing or post-processing. The core idea of our approach is to construct the lane graph incrementally by introducing one new node at a time and explicitly defining its topological relationships with all previously added nodes. To illustrate, consider the addition of node 4 as shown on the right. Before this step, the adjacency matrix contains only the first 3 rows and columns, representing the existing topology among nodes 1, 2, and 3. x4, y4 are the coordinates of node 4. We expand the matrix to include the 4th row and column to encode node 4's connectivity. In the updated matrix, non-zero entries in the 4th row indicate direct outgoing connections from node 4. For example, the element in the 4th row and 2nd column means node 4 connects directly to node 2, without any intermediate nodes, which we denote as the centerline segment 4 to 2. Conversely, non-zero entries in the 4th column represent incoming connections. The element in the 2nd row and 4th column means node 4 can be reached directly from node 2, denoted as 4 from 2. The new sequence, formed by concatenating the previous sequence with the information of the current node, represents the subgraph of all nodes present so far. By repeating this process iteratively, we ultimately obtain a complete sequence that fully represents the entire lane graph. As shown on the left, the figure visualizes this incremental construction over 6 steps, displaying both the evolving subgraph and its corresponding adjacency structure at each stage. The order in which nodes are added follows a depth-first search strategy. The figure shows the sequence structure of SeqGrowGraph. Each node's sequence includes its shape, connected node indices, and Bezier control points of the center lines. By concatenating these, we form the target sequence. This serialization offers a flexible yet compact representation of topology, preserving key graph-level information. Next, we discretize positions and control points, excluding special tokens and indices. Coordinates in the ego vehicle's frame are mapped to discrete bins, each assigned an integer. We employ a BEV encoder to transform surrounding camera perspective view images into BEV features. Subsequently, a transformer decoder generates tokens of the target sequence. Thirdly, experimental results. We evaluate our method using 2 widely used autonomous driving research datasets, NewScenes and Argoverse 2. In addition, we employ metrics including landmark precision recall and reachability precision recall. Here, landmarks mean topological nodes. The final results show we outperform previous methods in both quantitative metrics and qualitative visualizations. Finally, conclusion and future work. These are our core contributions. We propose a novel, flexible framework and demonstrate state-of-the-art performance. These are our future directions. If you are interested in any aspect of this work, we would be happy to discuss. Please feel free to contact us at any time. Thank you for listening.